electrons, then list the number of bonds. Didn't mean to smack you. Okay, so you're going to do that with each. So that's really like steps 1, 2, and 3, right? Remember that the number of valence electrons is just the group number. So the top of the periodic table, that capital A, that tells you the number of valence electrons. You don't have to figure them out. That is the number of valence electrons. And remember, the number of bonds would be 8 minus the number of valence electrons. So over on that far right side, I wrote carbon's always going to have 4 bonds. Nitrogen and phosphorus are always going to have 3 bonds. Oxygen and sulfur are always going to have 2 bonds, right? Some combination, single bonds or double bonds or triple bonds, to give them those total numbers. And remember that hydrogen, fluorine, chlorine, bromine, and iodine only ever have 1, right? So I always add those last, right? When you're building a molecule, hydrogen, fluorine, chlorine, bromine, iodine, you're always going to use those ones last because they're always kind of like the filler. They're the ones that just form a single bond to link to your central atom. So then really, like the steps start with step 4 because you kind of know the rest. So you'll always start with the atom that needs the most bonds. You place it down with its valence electrons. Then you're going to put the atom needing the most bonds next to this first atom and form a pair. Make sure that you add the valence electrons of the second atom you place down, and then you just keep doing that. Always, though, step 6 says continue adding atoms to the molecule. Always add to the atom that needs the most bonds. So if we look at CH4, so down at the bottom I wrote 1 carbon, 4 hydrogens. Carbon has 4 electrons, needs 4 bonds. Hydrogen has 1 electron, needs 1 bond. So when I go to add this, always going to start with carbon. If carbon is in the molecule, you always start with carbon because carbon is always going to need the most bonds because it needs 4. So now I've got 4 hydrogens, and if you look, you should see, well, I know hydrogen, I have that up there. Hydrogen is sort of this weird exception because hydrogen has 1 electron and only needs 1 bond. It doesn't follow the octet rule because hydrogen with 2 electrons is just like helium. So that'll make it like a noble gas, and that makes it stable. So I have 4 hydrogens, each with a single electron, and so they will form a covalent bond. Notice when I do this, you always want to have like the electron from one atom and the electron from another atom end up between so that shows that they're being shared. Okay, so you're not going, really? So don't put, like if you put your hydrogen down, you don't want to put the dot down here, right? Because that doesn't, see how I have it drawn there, that second red hydrogen, that's not paired, okay? So when you go to do the Lewis dot, make sure that you put the dots between the atoms that are sharing the pair. I just noticed that in lab that was kind of like a common thing that people were doing. So you're going to then put a hydrogen dot. So now you can see that fulfills, hydrogens have 2, carbon has 4, and the Lewis structure, remember, just replaces the shared pairs with dashes. One shared pair turns into a dash. Hydrogen was another example that I did, and so hydrogen, H2, exists in nature. So hydrogen, H2, 2 hydrogens, 1 electron each, 1 bond. So in this, I would just link the 2 hydrogens, making sure that the electron pair goes between the 2 of them. And so this one would end up with just a single covalent bond between. Going across, looking at oxygen, down at the bottom, oxygen exists as O2. So that means that there's 2 oxygens, 6 electrons, 2 bonds for each of them. So I put the purple oxygen down first and see the 6 dots. It doesn't matter where you put the dots. It's just important that 2 sides have 2 electrons, 2 sides have 1 electron, right? So that's how you spread out your 6. So when I add my second oxygen, I pair 1. So see where the red and the purple go between to form a covalent bond. And then I've got to add the rest of the red oxygen's electrons. So do you see that there's 6 dots for the red oxygen? Always make sure, don't forget to add those valence electrons, not just the ones that are paired, but you got to add the other valence electrons in there too. So that was just another thing that I saw in drawing the electron dot structures, is sometimes people just randomly left off valence electrons. Always make sure that not only do you form the pair, but add the dots that belong to that atom as well. So notice there, I'm done, right? So the last step says you only form multiple bonds if it's necessary after you place all of your atoms down. So for O2, I put 2 oxygens down. I've added all of my dots. So I have to form multiple bonds because I don't have any other choice. And so the multiple bonds will then, any single electrons will get moved so that they're between the atoms that don't have 8, right? So if you look at purple oxygen has 7, red oxygen has 7. So this dot has to move in between. This dot has to move in between. So that is going to form the double bond. Okay, so I'm going to erase this one purple dot. Maybe. Oh, I can't erase it because it's on the other thing. So that one's going to go away. So I'll have to, please don't go blank. My whole screen went blank and I had to delete everything last night. It's like, this is what I get for calling IT. All right, so I moved those and now they are going to go one in between and then the purple one slides in between. Seriously. Yes, duplicate, connect. Just love technology. Love it. Mm-hmm.
So, just like for when we take the exam, do we need to have like 2 different colors of pencil?
If you feel like, so there's, if you feel like that helps you in counting and numbers, then I'm fine with that, okay? But there's no, if I asked you to draw these, it will be an example that we have done in class. It is not going to be something you're like, I've never seen this before, okay? You are not going to see like having to draw Lewis structures. It is going to follow like the examples of ones that we've done. So practicing those is really going to make the bigger difference. So you're not going to see ones that you're like, I've never seen that one before, okay? Just expect these ones, because these are really good kind of classic examples of why double bonds, why triple bonds end up being formed. So now you can see it, because I finally got back up. So notice that, and it doesn't matter if like, see how it looks like 2 red dots are above and 2 purple dots are below? I don't care. You could put your 2 red dots this way, your 2 purple dots that way. I don't care. Just make sure that there's 2 purple dots and 2 red dots somewhere between the 2 oxygens. As long as you have 4 dots, they could be this way or they could be this way. I've even seen people put like 4 dots all in a row. I really don't care, okay? The key thing is they need to have 4 dots between those 2 oxygens, because 4 dots represents a double bond, right? So now if I take this, can you see that this oxygen has its 8? There's 4 that are shared plus its own 4 non-bonding pairs, and then the same thing with this one. So now when I draw this, I would put O double dash O, and I keep those non-bonding electrons because those non-bonding electrons end up having an effect later, okay? But those dashes, every dash represents a pair. So then then this one. So nitrogen is the most wonderful because it's got 5 electrons, needs 3 bonds. So if I look at this first one, if I look at the purple one, I put down the N, I put 5 dots. One side needs to have a pair, the other 3 sides should be single, okay? It doesn't matter which side has the pair. You might put it on any side, doesn't matter to me. But now when I go to put my nitrogen down, the second one, make sure that you put, oh, it's purple. Make sure that you put the second atom and pair it with a single purple electron. So you wouldn't want to put your second nitrogen on top where there's already 2. Make sure that you always like join them to a side with only 1. I did see that too. I saw where somebody was like trying to link one where they had 2 dots, and they're like, well, there's already 2 dots there. And so then they were putting a 3rd dot. And so no, make sure that when you form a covalent bond, always link it to the atom where there's only a single dot present. That way you can form the pair, okay? So like this. So I would put it to here, 1, 2, 3, 4. The 5th one, I'm going to be pairing, okay? So notice now there's 1 pair. Don't forget to add the other valence electrons. If you've got 5, you've got to have 5 dots that belong to that red nitrogen and 5 dots that belong to the purple nitrogen. So that's it. Now I'm done. So then that last step 7, I have to form multiple bonds because I'm done. And like I put my red nitrogen way too close. I got to move it over. Sorry. It's going to need a little bit more space. So there. Okay. So now, do you see these two aren't paired? So I know that I'm going to have to move one purple electron and one red electron between the two nitrogens. So this one's going to disappear and move here. The purple one will move over. I can't do it. It won't let me because I'll have to close. Then going through I'm going to have to do it again. So do you see that I still have like single electrons on the outside? So those ones are going to have to move as well. So I'm going to move, erasing, changing that one, moving it as well. So now I've got 3 purple dots and I will end up with 3 red dots between. Okay, they look pretty close, but there's 3 of them there in between. They won't let me erase the purple dots. Just because. Now, when you go to do the Lewis structure, what will it do? Please come back. Blast me. I'm just going to erase these and come back. It should be, it's reconnecting. I don't think I'll have to go through the whole thing. Okay, so there, I went back and erased them. So now they're gone. I basically just moved them in between. Any singles, when you form a double bond, those single electrons go between the 2 atoms that need to share more bonds, okay? And they always move, right? So you will have to that's where a pencil is helpful because that way you can erase them and move them. And if you find like the colored pencil things, then that helps you kind of keep track of your colors. You always end up, the purple nitrogen should have its purple dots still around it. So you shouldn't end up with purple dots around the red nitrogen. They're going to end up still connected. They might belong to the nitrogen or they might be shared, but they're still part of the purple nitrogen's electron number. So when I get done this now, 1, 2, 3. So you see 3 dashes. Those 2 dots above each nitrogen, those are their non-bonding electrons. It doesn't matter where you put them. They could be there, they could be here, they could be here, they could be like this. It doesn't matter, just so long as there's still 2 dots around each nitrogen that belong to nitrogen exclusively. But those 3 dashes, each one represents a pair. So then, last one. So water. Water's another one that's really common. Water, H2O, I made the list down here. 2 hydrogens, 1 electron, 1 bond. And then I have 1 oxygen, 6 electrons, 2 bonds. So that's kind of the first step that you do in going through. Which do you start with? Oxygen. I thought you said, when you said O, I was like, oh. I didn't know if you were going, oh. All right, so where I'm going to start, you're going to put oxygen down and just put 6 dots. Doesn't matter where the dots are, just so long as there's 2 pairs on 2 sides with single dots on 2 sides. So now, can you see where your empty spots are? So where the single dots are is where you need to form covalent bonds. So I'm going to add, and in my example, where are you going to put the hydrogens? So you're going to put 1 here and add the dot, right? So now I'm forming a pair. So you should end up with 1 of each electrons from the oxygen, 1 from the hydrogen being the pair. Same thing here. Pretty straightforward, all single bond. You always try to just do single first. Don't worry about double bonds or triple bonds till after you get everything down. So now if I go back to the Lewis structure, just changing the shared pairs to dashes. In the next chapter, they go away from the dots. Everything's going to be dashes. It's just because it's so much faster than having all those little dots everywhere. Okay? Everybody got that? Anybody need a second? Okay. And like I said, I saved this, right? This will be saved as the chapter 3 marked up PowerPoint in Moodle. So you could always download this PowerPoint. It's got all of my notations on it. So if you're ever like, oh, I need to see what she wrote because I didn't write this right, you can always go back and check. So you don't always have to watch the video or anything like that. This is being recorded, so I do have the lecture videos are posted. They look like little globe things. They're YouTube videos, and it's just the entire class. I do crop out when I give you time to work on stuff, but other than that, I just leave that. I leave it open. And sometimes, a lot of times, you can hear people asking questions, so that's kind of helpful too, especially if you miss a class. So if you miss a class, you can go back and watch this and literally take notes as if you're in the class, because everything is sort of like written as I'm saying it, just as if you were in the class. Okay, last three. So carbon dioxide, formaldehyde, and then cyanide. These are the three. You would have them also on your periodic tape, on your PowerPoint if you printed it. It's just in a kind of a different form. I just thought I'd give it a little more space. So CO2, I already listed. What page? Who has theirs? It's right there. What page is that? 18. Slide 18.
Okay, I was way behind.
Do you see it? So like the previous slide did have CH4, H2O, had those ones in it. And so I just like wrote all those steps out and then just put it at the bottom. I didn't really change it except for adding those steps, if you find that helps. So in this one, first step you do, you write the names of each of the atoms in the formula, write the number of electrons, remember it's the group number, write the number of bonds. You always want to make a total of 8, other than hydrogen, which only wants 2. Then I'm going to start, so 1 carbon, 2 hydrogens. Which do I start with CO2? I'm going to start with the carbon, right? And initially, always spread out your valence electrons, so 1, 2, 3, and 4. Then I'm going to add and the atom that needs the most bonds next. Well, I got 2 oxygens, so either one. So 1, 2, 3, 4, 5. Just make sure that you pair. You pair one black electron from the oxygen with the single red electron for the carbon. So I made a covalent bond. Notice I wrote them this way. That's okay. You can do it this way, you can do it that way. Doesn't matter. The key thing is, do you see that the red and the black dots are between the carbon and the oxygen? Okay? Because I know that sometimes they're like, what? Why is it like that? It can be like that. The key thing is it needs to be in between. Okay? So whether you write it like that or if you write them so they're up and down, that's okay. Just make sure they're in between those two. So now I've got to add the other oxygen. Doesn't matter where I'm going to add it. I'll just put it on this side just for the convenience thing. And again, I could write it, ooh, what is that? I could write it like that. That would not be wrong. Do you see that my black and my red dots are between the carbon and the oxygen? That's the most important, not how they're written. If they're written side by side or if they're written above one another, that doesn't matter. The big thing is you want to make sure they're in between those 2 atoms. So either one of those is perfectly fine. But do you see that now I've used them all? I've put all my carbon electrons, I've put all my oxygens and electrons. So you see that they're still singles. That's when you know you've got to do multiple bonds. Okay? So oxygen, if you count 1, 2, 3, 4, 5, 6, 7, counting the red carbon electron. So I know I'm going to have to form 1 more bond for each oxygen. So I'm going to have to do a double bond for each oxygen. So I'm going to take and move this one and move this one. So 1 black electron from my left oxygen, 1 red electron from my red carbon are going to end up moving. So I'm going to move them. So one's going to end up here and one's going to end up here. Okay? So now that oxygen, if you look, you see that it's got its 8. Okay? So that left oxygen is now stable. But now if I look at my right oxygen and my middle carbon, carbon now has 7. Oxygen on the right only has 7. So that tells me to pair those remaining unpaired electrons. So that means that that one's going to move in and this one's going to move in. So those, once I move these and put them between, then that indicates, and so look at this, the way I've written this one, that would be fine too. So notice in this, the one on the left, it looks like the black dots are above the red, and then on the one on the right, the black dots are above or next to the red. It doesn't matter. Just key thing is, do you see there's 4? There's got to be 4 dots between the carbons and the oxygens. Okay, so having them this way or having them that way, it doesn't matter. Okay, because I know sometimes people get like hung up like, wait, they're not side by side. They don't have to be. Just make sure they go between the atoms that are sharing them. That's the most important thing. Notice also, do you see that the black oxygens still have their 6 electrons around them? Some are being shared, some are non-bonding, but they're still connected to them. So I didn't like take these red carbons and move them over on this side of the oxygen so they're not anywhere near the carbon. So the 4 carbon electrons still are attached to the carbon. They're just being shared. So now when you look at it, you can see that you have your total of 8, and then that carbon shares all of its total of 8. So when I go to draw this, I'm going to have 2 dashes between oxygen and carbon on both sides. The non-bonding pairs, 2 pairs of non-bonding electrons belong to the oxygens. CH2O, 1 carbon, 2 hydrogens, 1 oxygen. Which one do I start with? If carbon's in the molecule, you always start with that first because carbon needs the most bonds of all the nonmetals. So carbon always gets listed first. Which do you add in next? So that then, okay, so I'm going to add oxygen in next. 1, 2, 3, 4, 5, 6. So now I formed a pair between carbon and oxygen. That's the black and the red dots, so that forms your covalent bond. But then I've added the other 5 red dots to represent the total of 6 valence electrons for oxygen. So I'm not done yet because I still have some. So what am I going to add next? So now I'm going to add, so now I'm going to add, when I go to add hydrogen, do you see that I have 3 empty dots around the carbon and 1 empty dot around the oxygen? The rule is always add to the atom that still needs the most bonds. So which would that be? Carbon. So you see carbon's got 3 empty dots. That's how you know. Because sometimes people are like, well, where do I put them? Should I just put them on the oxygen randomly, just put them anywhere? No, it's not a random thing. So I'm going to add 1 hydrogen forming a pair. And then I'm going to add the other hydrogen to what? Still adding it to the carbon because see how carbon still has 2 empty spots? Oxygen only has 1. So that's going to dictate that I got to add the hydrogens to the carbon because they need the most bonds. Now I'm done. I've added everything and I still have unpaired electrons. So see the single dots? Those are going to move where? Between carbon and oxygen. They get moved. Can they get put between carbon and hydrogen? No, because carbon and hydrogen only are going to ever have a single bond, 2 electrons. So the only option is to move them between carbon and oxygen. Doesn't, yep, yep. So she was asking if I did this. Yep, that's perfectly fine. Okay, and remember, it would still also be fine if you did that. Don't let that throw you, right? Remember the 2 dots? It doesn't matter if they're this way or that way, as long as they're between the 2 atoms. That's the important thing. Okay, so I got to move. So I'm going to move this one, and I'm going to move that one. I'm going to move them so they're now between the carbon and the oxygen. Please don't kick me back up. Because it just stops letting me change the ink without doing all the craziness. All right, so I'm going to erase these so that now it won't let me erase them. So that one and this one. So I'm now just moved them so that they're in between. These are now gone. There. And so that leaves you then. Now can you see 8? If you look at oxygen, do you count 8? You look at hydrogen, can you count 2? You look at carbon, can you count 8? Yes? All right, then you know you're done, right? Because remember, hydrogen will only ever have 2. All the other ones have to have their 8. And that's where, when you go back to do the Lewis structure, I'm still going to keep my non-bonding electrons around the oxygen. Notice carbon doesn't have any non-bonding electrons. Neither does hydrogen. They never have, never will. Last one. So last one, which do I start with? Carbon, because carbon is the one that needs the most bonds. And then I'm going to add Nitrogen, because nitrogen needs 3 bonds. So don't go according to the formula, because I've seen some people go, okay, well, I'll put hydrogen down first, then the carbon, then the nitrogen. Don't do that, okay? Always put down the one that needs the most bonds, then add the one that needs the most bonds next. So this is going to tell me that, okay, I've got to go 1, 2, I'm going to make my pair, 3, 4. Put them side by side just to like keep you guessing. Okay, so I've now got my 5 dots, right? Remember, so that nitrogen's got 5 valence electrons. So once you make your pair, you still got to add 4 more dots. Don't forget to add the valence electrons when you drop the atom down. Pair one of them, add the other valence electrons on the other sides. Now I'm going to add the last one. Where do I add it to? Because it has the most empty dots, right? So carbon still has like 3 empty dots, 3 that need pairs. Nitrogen only needs 2. Everybody see that? So that dictates that the hydrogen has to go over here. And it would not be wrong if you put it above the carbon or below the carbon. It just has to get connected to the carbon. They can be above and below. They could be side by side. That would still be fine. I'm done. I've used my hydrogen, my carbon, my nitrogen. So now you know you've got to form at least a double bond, right? And so that means that these 2 are going to have to move. And then see that I still have 2 more pairs. So I'm going to first move this one and go to the red and go to the blue. Right, so that's a double bond. I'm not done because you still see those single electrons. They've got to move. And remember, they're always going to move in between the atoms that they belong to, right? So since I've got a red one and a blue one, they're going to move between the red and the blue atoms. They're going to move between the carbon and the nitrogen. So this one's going to move and this one's going to move, which is then going to take them out. Oh, not that one. Well, let me put those dots back. There. So do you still see 4 red dots? Those are carbons. 5 blue dots, those are nitrogens. 1 black dot, that's hydrogens. Okay, so they're still all there. I've just had to rearrange them. Can you see that nitrogen has 8? 6 are shared plus 2. Carbon has 6 are shared and 2 is shared. That's 8. Hydrogen has its 2. If I switched it to the Lewis structure, 3 dashes for those 3 pairs of electrons that are shared. Lexi? So each line is 1 pair of dots. Okay? So see, like in all of them, if there's every pair becomes a dash. So if I have a single bond, it's 1 dash. If I have a double bond, it's 2 dashes. Triple bond is 3 dashes. So that's why between C and N, there's 3 dashes because there's 6 electrons or 3 pairs. Okay, just remember every dash is a pair of electrons. Good. Okay, so maybe that like helps a little bit in moving them out. So now we move on to, and really these are like the big ones. These are the ones that if you're familiar with how to draw those examples, practice those examples, those are the ones you'll see on an exam. Okay, you're not going to see anything that's like very hairy and scary and like completely abnormal looking. These will be the ones if I ask you to draw a molecule. Okay, naming. So when we talk about covalent molecules, what they found is because atoms or electrons are shared, they can be shared in lots of combinations. So for example, you have H2O. So everybody says, oh, I know that, that's water, right? 2 hydrogens and 1 oxygen. Then you know that it is like this, right? So we drew that one. But H2O, and you can have a molecule of H2O2. This is actually hydrogen peroxide. If you've ever bleached your hair with peroxide, this is hydrogen peroxide. And this exists as a covalent molecule as well. And here's what it looks like. It is when 2 oxygens form a single bond. And then they form a single bond to each hydrogen. You can do that, okay? So we could like have different combinations of nonmetals and hydrogens. Whereas with sodium chloride, remember, it's only NaCl. You can't make NaCl2. because remember they're ions and you swap the charges, you can figure out there's only one possible formula for a typical ionic compound, but that's not the case with covalent. So then they were like, well, we can't like keep the same name. We couldn't just call this hydrogen oxide. Remember like sodium chloride? We can't call this hydrogen oxide because how will we be able to tell the difference between H2O and H2O2? So this is where Greek prefix numbers come into play. So they're like, well, then we've got to add numbers to show in a formula how many of each atom there is. So if you have 1, you use the term mono. If you have 2, you use the term di. So just knowing that, we can name these 2 molecules and see that they have different names. The genius of this is they always use the whole name of the first element, just like with ionic compounds. First part of the second element plus IDE. So remember how sodium chloride, so use the whole name of sodium, first part of chlorine, chlor plus IDE. You're going to do the exact same thing with covalent molecules, but you got to make sure you add a number prefix. Bless you. So H2O becomes what? If there's 2 hydrogens, you got to call it di. Whole name of the first element, so it's hydrogen. This is dihydrogen. And there's only 1 oxygen, so you got to call it monoxide. So some people are like, well, it's monooxide. Well, when there's 2 vowels like that, they drop one of the O's. So instead of monooxide, they just say monoxide. So that's what water is, okay? Dihydrogen monoxide. It sounds much more fancy otherwise, but that's its common name is water, okay? So then I told you hydrogen peroxide is H2O2. So what is its fancy name? Dihydrogens dioxide. 2 words. Both of them would have to have the di in front of them. So here's all of them. Okay? So here's all your number prefixes. And I will add a couple because occasionally eight, 9, and 10. 1 is mono, 2 is di, 3 is tri. So di, tri, those sound pretty familiar. Mono doesn't even sound all that bad. Most people think mono, okay, I can remember that's 1. But tetra's the one that sometimes gives people fits because tetra is 4, and that's a Greek term, right? So if it was Latin, it'd be quad, but it's Greek, and so that's where the term tetra. And I'll tell you that the way that I always remembered it in college is because of Tetris. So I don't know if you remember playing the little game Tetris when you were a kid. It was like on the little tiny flip phones. You could play it. And so it was always blocks of 4. So you either had a square of 4 or 4 in a row or an L, 3 and 1 over. And so you were trying to they would fall and you had to position them to keep it knocking out the layers. That's where that comes from. So the name Tetris comes from groups of 4. So you remember tetra is 4. But then from there, penta, hexa, hepta, octa, nona, deca, those all follow what? Shapes, right? Like a pentagon is 5, a hexagon is 6, an octagon is 8. So from here down, these are all kind of like geometry shapes. So most people are a little more familiar with an octagon or an octopus. And so it's easier to remember those ones. You just kind of if it's been a while since you've thought about geometrical shapes, then go back and review pentagon, hexagon, heptagon, octagon. So those ones kind of follow. So I would say tetra is really kind of the weird one. So if we had N2O, NO, here's one of the exceptions. You don't have to use mono if the first element only has 1. You can leave the mono off. Other than that, you name the number of each element and it always goes in front of the name of that element. So if the first element has anything but 1, you're going to put its number prefix. The second element, no matter what its number, you always put its number prefix. Okay? So if I have NO, what would you call that? N is nitrogen, and there's only 1, so I do not have to put mono. You just say nitrogen but then there's only one oxygen, so I would have to say monoxide. Okay, so that one shows you the exception. If the first element is a 1, you don't have to put mono. But the second element, you always have to. So then N2O, dinitrogen, and, no, what do you got to put in front? Monoxide. NO2, dioxide. And these are actually all actual combinations that nitrogen and oxygen can make. So when they started realizing, wait a minute, there's a lot of ways nitrogen and oxygen can combine, they had to come up with a way of being able to identify one molecule from another. That's where the Greek prefixes came. Because otherwise, you just call all these nitrogen oxide and be like, I don't know which one it is. You got to be able to tell what the formula and the name comes from. Okay, so N2O4, dinitrogen, whole name of the first element, and then, and so here's an example, since it's tetra, if the element begins with an O, you'll drop the A. So instead of tetraoxide, they'll just call it tetroxide. And if you left it, I would not mark that wrong, because that's fine, okay? But tetraoxide or tetroxide, it doesn't make a huge difference to me. But everybody knows this one. Carbon dioxide, right? CO2, okay? So carbon dioxide, that's where its name comes from, though. That's why it has that dioxide. Because we can also have this. And what's that? Carbon monoxide. They're very different, okay? Carbon dioxide you inhale, carbon monoxide will kill you. Okay, we'll talk about that in chapter 5, because that's a chemical reaction thing. Okay, so that's the reason that you've got the number prefixes. So, the next question is, well, how do you tell the difference? How do you tell the difference between ionic and covalent? How do you make sure that you name things correctly? So go to your worksheet, okay? So go to that sheet that I gave you, the short little handout. I got a couple. If you forgot yours, I do have like 2 or 3 left up here. You can come and grab one. Okay, I have saved this, and it's actually posted in Moodle, so it says like ionic and covalent naming practice sheet. So I have this for you to be able to use. So you tell me the first one. The first part down here, and I actually because I use this to print. So look, there's actually there's some blanks. So like if you wanted to print this and then practice and check yourself kind of thing, then it'd be another way. Here's where all the answers are, right? So I got the answers, and then I have a sheet that's got, and then the rest of that page has the exact same one and just blanks. So it'd be a good practice if you feel like you're having a challenge. So now you tell me, what is the rule for naming ionic compounds? Okay, whole name of the metal. Whole name of the metal. And? Yeah, so you don't use the whole name of the second element. What do you use? The first part, okay? Whole name of the metal. First part of the nonmetal plus IDE, always, okay? Unless, what was the one exception? So remember, if you have transition metals, so transition metals were chromium, iron, and copper. What do they require? A Roman numeral, right? So chromium, iron, and copper use a Roman numeral to indicate the charge. Not the number of ions, or number of atoms, because I did see that in lab yesterday. Some people were looking at like iron 2. Okay, that's an iron with 2 of them. No, that means it's iron plus 2, right? So there's a couple, I think there's one in there too. What's the other fancy one? The other fancy exception It's really a challenge being a left-handed person. The other part is polyatomic ions. So with polyatomic ions, these are things like the sulfate, the nitrate, the chlorate, the phosphate, the carbonate, the hydroxide, and the ammonium ion. Those 7. It's just those 7. Those are the ones I gave you in the box. So to answer some of these, you may end up having to look for that, find that in your notes and answering them. Polyatomic ions, you just use the name of the polyatomic. So if there's a polyatomic, you just use its name. You don't have to change to IDE. So if there's a phosphate in your formula, it just ends in phosphate. You just use the name of the polyatomic. Okay? You don't have to do the IDE thing. So here's an example. So Mg3N2. So what would its name be? Yes? Yeah? Magnesium what? Nitride. No number prefixes in ionic. So you may want to put a note there too. There's no number prefixes because this is the only way magnesium and nitrogen can combine. Because remember, they make charges, you swap the charges. There's only one formula between magnesium and nitrogen. They won't combine in any other way because they swap electrons, right? There's a transfer of electrons that occurs. Ions are formed. That is why the formula is like defined. It can't be any other way. Magnesium nitride. Okay? No Greek number prefixes. So how do you figure out the formula for calcium iodide? What do you have to do first? Okay? So you got to first write down what? Symbol first. Then what's the charge on calcium? +2. And you know that because it's in group 2, right? Calcium's in group 2A. Top of the column tells you the number of valence electrons, and that tells you how many it will lose. So calcium is in group 2A, becomes a +2, and then iodide is what? I, and it's in group 7. 8 minus 7 tells you it's a -1. Right, so everybody remember, that's how you figure out the charge. Now what are you going to do? Do the swapping. The charge on the calcium tells you how many iodine. The charge on the iodine tells you how many calcium. So this ends up being CaI2. Okay? Remember, the charge always goes up. It's like a superscript. So see where it's +2 and the negative? Those are always like up above the symbol. The formula always goes as a subscript. It always gets written down. Okay, so I saw that too, like some people putting the number from down and putting it up. You got to make sure that you keep those ones straight so you don't mix them up. Rules for naming covalent compounds. You're going to need to use number prefixes. And the only exception is unless mono is in the first element. So no mono in first element. But other than that, mono, di, tri, tetra, penta, going along. Okay, you're going to add number prefixes. So how much of the first element do you use? Whole name. So now you really understand why I told you had to learn the names of those elements. Whole name of the first element. And if that's part of what you're struggling with, you need to just sit down and just write them. Like write names and formulas, just write them. Because you're going to have to write them and you're not going to have the names and symbols. Those ones, just those 30, I won't give you any except those 30. Don't have to learn the names and symbols of any except the 30 I gave you. And those are listed in the PowerPoints in Chapter 1. Okay, so if you go back to Chapter 1, it's in that periodic table. That one periodic table has the names and symbols listed. So if you don't have all of those down, you do need to work on those. That would be like a goal for the weekend. I gotta learn them. Okay, all right. So whole name of the first element plus second element. What do you use? first part of the second element. Plus, and then you add IDE. These will always end in IDE, always, okay? And this only holds for binary. So binary covalent molecules are ones that only have 2 atoms. So that way we've just got this one and this one, like CO2, N2H4, okay? We just have 2. So examples, N2O4 would be what? Dinitrogen tetroxide. Now, if you're given the name, I think this is the easiest way to do the formula. So this one, phosphorus trifluoride. What would be the formula? PF3. So since it just says phosphorus, you know there's only one. So you got to remember phosphorus is P. Stop. Okay? And then trifluorides that you say, oh, tri is 3 and fluoride is F. So I know that that's PF3. So notice like the 3 is a subscript. Okay, 5 minutes. I want you to see how many of these you can write the names and the formulas from the names. You can talk with your little elbow partner people. Last one, and maybe you want to do the last column first, ionic versus covalent. How do you tell ionic? Look at the first element. If the first element is a metal, it's ionic. If the first element's a non-metal, then you know it's covalent. So how do you tell metals and non-metals? Zigzag line, right? So if the first element's over here, it's a covalent molecule. If the first element is any of these, then it's ionic. So go through, do those. It's 10:21, you have till 10:26. Okay, and there I'll put the list. I'll put sort of like the rules up for you. That way I can do roll, because I haven't done that. Really, I'm trying to be like on top of this. Right, because this is a metal. So that's like to tell the difference. Look at the first element. If it's a metal, then I know it's ionic. So that means the second one is ionic because there's a metal. So I know that's ionic. So what about the third one? Covalent, because this is a non-metal. Everybody sees sulfur. Find sulfur. It's to the right of the zigzag line. That's how I know that's covalent. Potassium nitride. This is a. Then PBr. Non-metal, covalent. Pentanitrogen, non-metal, covalent. Cu3P, ionic, because that's a metal. And then ammonium phosphate. What is the ammonium? It's a what? Ion, right? So anything with a polyatomic is always ionic. Just note to self, if there's any, and I put that one up there on purpose, any molecules with a polyatomic ion have to be ionic. They're all going to involve some kind of charge. And so, because this, polyatomic, ion, right? So polyatomics are ions. So that's how you know that's an ionic compound. Okay? So now let's go back and we're going to do the first one. So from the name, iron 3 sulfide. For the formula, I suggest you write it out in 2 steps, okay? Write out the charges, then do the swapping. So iron 3 tells you what? That it's Fe plus 3, right? So remember the Roman numeral tells you the charge. Iron 3 is iron plus 3. Sulfide would be an S with the minus 2. So I first write the elements, assign the charge, now swap them. So that means my formula is, yes. Everybody got that? Okay? If you didn't, it's just really just like, got to remember what that Roman numeral tells you. So next one, Ca parentheses NO3 parentheses 2 is calcium, because it's ionic, no number prefixes. I heard it, nitrate. right? NO3, that's a nitrate. So especially if you see, you can also put a note, if you see things in parentheses, you know they're a polyatomic, okay? Things in parentheses, or if you see a nonmetal with a bunch of oxygens after it, and there, so the other things, notice there's three elements in that formula. If you see 3 elements, it's a polyatomic, okay? Because all these other ones, they're binary. So binary means they only have 2. So you put yourself a little note. If you see 3 elements, you know there's a polyatomic in there. Next one. S4O2 would be tetrasulfur dioxide because it is covalent. So I've got to use the number prefixes when I have something that's covalent. Next one, potassium nitride. K, what's its charge? +1. I, what's its charge? -1. Oh, sorry, it's nitride, not iodide. I was looking at iodide. N, and it's a -3, right? So put your element, put its charge. Now you do what? Swap them. So now the formula is K3N. Right? The +1 of the potassium tells you there's 1 nitrogen. The -3 of the nitrogen tells you there's 3 potassium. Next one, PBr3. And then what's the rest? Tribromide. Right? First part of the last second element plus the IDE. Covalent will always end in IDE. Okay? Pentanitrogen trihydride. So this is what? And what? 5, right? Penta, like a pentagon. So 5 nitrogens and 3 hydrogens. So hydride is one that sometimes throws people. Remember, there's hydride and then there's hydroxide. Hydroxide would be a polyatomic ion. Hydride is hydrogens. So it's hydr plus ide. And you haven't really seen that much because hydrogen doesn't form those ionic compounds. So we haven't done the naming using it. Okay? So that one would be H3. Cu3P. Okay, so it's copper and phosphide. But I have to add, it can't be a 3. Copper can only be a +1 or a +2, right? Huh? How do you know? Remember the copper 3. Copper with 3 is not the charge. It's like the most common mistake with transition metals. Let's go back and do it. You don't know the charge in the copper. So that is, so phosphide is a -3, right? That doesn't look like a -3. Let me fix that. So the phosphide's a -3 because it's 8 minus 5. So do you see that the -3 of the phosphorus matches the 3 of the copper? Do you see those match? Okay. How many phosphorus does this formula have? 1. So, well, because if it's just P, it's 1. Cu3P. Do you see that if this would be a 1? Remember, you don't write it. If there's, you're kind of doing like a reverse swap. So you know, so you agree H2O has 2 hydrogens, 1 oxygen. Okay? So Cu3P has 3 coppers and 1 phosphorus. So there, reverse swap. That means this is a plus and this is a -3. So remember the formula, it's like a reverse swap that you would do. The number of coppers tells you the charge on the phosphorus. And as long as those match, then the number on the nonmetal tells you the charge on that metal. Okay. So notice how they are like a reverse swap. So that's how I know this is a +1. So it's copper 1. Copper 1 phosphide. Okay, last one, ammonium phosphate. So ammonium is NH4 and its charge is something you got to make sure you put on your study chart. A +1. Phosphate is PO4 and its charge is -3. So now when I swap this, What do I have to make sure I include? Parentheses. I'm going to have to put parentheses around any polyatomic that is more than one. So when I swap, which one's going to have more than one? The NH4. So I'm going to have to do NH4, put parentheses around it. What do I put outside? The 3, not a -3, just the 3. Remember, drop the sign. Because the phosphate has a -3 that tells me how many ammonium ions I have. How many phosphates? Just one. Because see that the ammonium is a +1. That tells me that there's only one phosphate. So it's just PO4. Okay? All right. So if you feel like, I don't know if I got this. Here's like, I'm going to save this. There's kind of like a blank page. So if you went to the library, you could print this page out, like cover up the answers and just practice them again. Just see like how well you can put them together. Saving it. Now we're going on. Moving. And we're going on. And there's actually, like, if you look back here, there's actually a couple of slides of just practicing. So if you're like, I still don't know if I got this. Well, here's some more practicing ones. So you could go through, check and see these are ionic or covalent. If you're stuck, if you're not sure, send me a screenshot, send me an email. Hey, can you tell me what these ones are? So these are ones that you can use to check. So this topic, the reason we really talk about this is we want to then apply, we're going to talk about shape so we can apply it to thinking about polarity. Polarity is how covalent molecules don't always share bonds evenly. So this, when we look at covalent molecules, you always draw them on a piece of paper and you agree it makes them look like they're flat, like methane looks like it's a T. So you got like carbon, one hydrogen up, one down, one left, one right. So it makes them really look flat. But if you were in lab and used little balls and sticks, then you knew or realized, oh, these actually have a shape. The whole reason that they have a shape is because these chemical or these covalent bonds are actually pairs of electrons, right? So you agree there's 2 electrons that go back and forth between the hydrogen and the carbon that they're shared between. So they go back and forth and back and forth. Well, but so do these. There's 2 electrons here. They're going back and forth between the hydrogen and the carbon. There's 2 electrons here, and there's 2 electrons here. So those 4 single bonds represent 2 negative electrons. Well, the electrons that are part of the bond, they're kind of stuck. They can't like go off and do their own thing because they belong to that carbon and the hydrogen. They go back and forth, back and forth. But electrons are what with other electrons? Are they attracted or repelled? They are. You know that opposites attract. So like charges repel. So that then means they're not going to get at exactly 90 degrees because you have a carbon atom and you have this whole circle area around it. The pairs, bonding pairs, want to get as far apart from each other as possible because they're negatively charged. So the bond is 2 negative electrons. They're going to repel any other bonding pairs, and that is why you end up with this shape. So carbon, and you'll actually see sometimes some of your book and maybe even in your mastering stuff, it might look like this. So this is the attempt to try and make CH4 look a little more three-dimensional. So in this, what they are saying is that the carbon, if the carbon was in the board or on the PowerPoint, then the hydrogen on the plane, I'll show you it this way. So the carbon and these 2 hydrogens with straight lines, they would actually all be like flat on the board, okay, or on the screen. But this one would actually stick out. This one would stick behind. So the wedge and dash is a way of trying to show some three-dimensional structure instead of just having them up, down, left, and right. So just remember the wedge means that it would be like pointing towards you. The dash would mean that it would be sticking back away from you. And doing this would actually give the maximum amount of distance between bonding pairs. But the distance is about 109.5 degrees. I won't ask you that. But that shape, the shape that it has, is called the tetrahedral. So what do you know about tetra? Tetra means 4. Can you see that there's 4 points? Okay, so it's kind of like a four-pointed pyramid, one hydrogen up, three kind of forming at the bottom. And so that's where the word tetrahedral, it means like four-pointed shape, comes from. A carbon, you can put a little note here, carbon with 4 single bonds. It does not matter what is attached to the carbon. If there's 4 single bonds, like it could be a carbon with 4 hydrogens, or a carbon with 4 chlorines, or a carbon with 4 bromines. If it's 4 single bonds, no matter what, it will always look like this, okay? It's always. Not a lot of times you can say that in life. It's always a tetrahedral. So then came the question, well, how do these other molecules, and we're really just going to look at the molecules we've talked about already, how do these other molecules look different, like water? How does water look different from CH4? How does NH3 look different from CH4? So ones that we have actually drawn and talked about, they said, well, it's all because of these bonding pairs that repel each other. So they came up with this like really fancy acronym. So a lot of people call it VESPER. I always learned it as the VSEPR, but I've heard people call it VESPER. This is just saying that bonding pairs repel each other, okay? Which makes sense because they're electrons. They're negatively charged, so bonding pairs repel each other. If the central atom has non-bonding electrons, they also have an effect. So let's look at those next. Here's the possibilities for carbon, though. So carbon, I said, if carbon has 4 single bonds, it is always going to be tetrahedral. But remember when we did CH2O? So we had a hydrogen here, oxygen over here. So in that one, in that shape, where carbon has a double bond and 2 single bonds, that shape is actually different from the tetrahedral. So in lab, it ended up looking like a little triangle, and it was flat. So that's where they came up with the name, the trigonal planar, which just means a flat plane with 3 points. Where have you seen that carbon with 2 double bonds? When they're oxygens. So remember we just did CO2, where you ended up with the 2 double bonds? That, because those double bonds are basically stuck between the carbon and their oxygen, but they want to get as far apart from the other double bonds. So do you agree if they got on opposite sides, that's as far apart as they can get? And that's why when you build this molecule in class, you saw that the double bonds ended up on opposite sides of the carbon, and you see how that looks like a line. So that is why they named this shape linear. This one here we actually did. Cyanide, right? So that carbon in the middle with the triple bond in a single, the triple bond, it doesn't matter if it's a double bond or a triple bond, the triple bond and the single bond still want to get as far apart as possible. The furthest that they can get apart is straight across, which also creates that linear shape. So they said, okay, we're going to look at non-bonding pairs too, because non-bonding pairs, when I look at NH3, which is one that you drew, when I look at NH3 and I look at H2O. So NH3, remember, has, when you did the Lewis structure, we just did that one, looks like that. It's a nitrogen with 3 single bonds to hydrogens, but there's that non-bonding pair. The non-bonding pair stays only around the nitrogen. And in fact, this non-bonding pair is 2 electrons, and it takes up space. And it has a negative or repelling effect on other bonding pairs. So what it does is it pushes those bonding pairs away, and that ends up creating a molecule that's a little bit raised. So instead of this being flat, like when we looked at here, do you see how this has 3 groups attached, the trigonal planar? Carbon has a hydrogen, then a double bond oxygen. Those 3 get as far apart as possible, like a little triangle. But if I look at ammonia, NH3, that's not the case. They can't get as evenly like flat and far apart because the non-bonding electrons repel the hydrogen bonding, and that creates a pyramid. So they call that a pyramidal shape. Even more extreme, they saw with water. So if I take water, which we've drawn, there's 2 pairs of non-bonding electrons with the oxygen. So that means this area has those 2 electrons, and this area has these 2 electrons, and they have an even stronger repelling effect on the bonding pairs. So this is why water, those hydrogens don't go straight across. They end up looking like this because the electrons like repel, pushing them and creating a bent shape. So that's why whenever you see water molecules, they always look like this. They never like draw them like straight across. They always give them like a little bend to them. They end up with this bent shape. It's all just because those non-bonding electrons. So that's kind of why we've kept track of non-bonding electrons as we've gone along. So on Tuesday, we will finish chapter 3 and be able to start chapter 4. We really just have to talk about like the ABN polarity, and then we're going to talk about moles of molecules and move on. If you have a calculator, make sure you bring it. It's the only math in this on this test.
Gotta go take one now.